Hello everyone. Can anybody hear me? Okay, let's wait for 5 minutes because maybe this is a rescheduled session. So we should wait for 5 more minutes. Let's see if anybody joins or not. After that, we will start our session. I hope everyone have received the link, but I don't know that why nobody has joined today. Okay, just we are waiting for 5 minutes. Let me check that link has been received by everyone or not. So link has been shared from the NPTEL team to everyone. I think everyone has received the link. So let's wait 2 more minutes. Okay. So good evening, everyone. My name is Amit Kumar Sharma, and today we are discussing the live session number 4 for the for the week 4 course content. And the course is Energy Conservation and Waste Heat Recovery, taught by Professor Pratap Kumar Dos and Professor A. Bhattacharya from IIT Kharagpur. And I am the TA for this course. So as you all aware that every week, like on every Friday, we are having a problem solving session in which we discuss the previous week's questions so that those will be helpful for you in your upcoming week's assignments. Okay. So actually last week I was not able to take the class, so this is a rescheduled session of the last week. Okay. Today we are going to discuss the week 4 course content. So I hope many of you will join the session and many of you will see the session later. Okay. So in this we will discuss some sample problems. Okay. So I will give you 2 minutes to solve the problems. After that, I will explain the solution. Okay, let's begin. And one important thing is that this session is being recorded, and the recording of this session and the NPTEL PPT, the PPT that has been shown here will be shared to you from the NPTEL team. So you can access the PPT and you can also see the video later. I hope my voice is clear and my PPT is visible. If any one of you is having any issue, please let me know. So the first question is that which one is true for idle Brayton cycle? And we have given 4 options. The option number 1 is it is commonly used as topping cycle. Second option is its efficiency depends on pressure ratio and types of gas used. It is used as a bottoming cycle. In it, heat addition takes place at constant temperature. So you have to go through all the options and you have to check that which option is correct. So let's take 2 minutes to solve this question. So this idle Brayton cycle is also called air standard cycle or Joule cycle. Maybe based on this you can recall it. Try to go through all the options. Try to remember the what are the TS diagram of idle Brayton cycle and in which way we can use it. Okay, so let's start with the solution. So the correct option is option number C. So basically the first and second statements are correct. So the first statement is that it is commonly used as a topping cycle. So yeah, it's commonly used as a topping cycle because we know that in idle Brayton cycle, it's a topping cycle. Okay, so the waste heat, that is heat rejected, we use heat rejected heat in a some bottoming cycle to produce the power. So like in combined cycle, we can use gas and steam turbine combined cycle. So gas turbine cycle will be based on a idle Brayton cycle, and the exhaust heat from the Brayton cycle will be used to generate the steam, and that steam will be used in the steam cycle or Rankine cycle. Okay, so that it's directly from the definition or from the basic concept, we know that the idle Brayton cycle is commonly used as a topping cycle. Second one is that its efficiency depends on pressure ratio and types of gas used. So yeah, it's very important. We have also derived the efficiency formula, and we know that the efficiency of idle Brayton cycle is depends on the pressure ratio and types of gas used, because it's also depend on the gamma, the index. So it's also depend on the type of gas used. Okay, sufficiency depends on the pressure ratio and types of gas used. The third one is it is used as a bottoming cycle. So as we know that because the Brayton cycle or air standard cycle is Joule cycle is the main cycle, so it cannot be used as a bottoming cycle. It will be used as a topping cycle, and from this as a topping cycle, we can use it. We can use the exhaust heat from topping cycle to run a other bottoming cycle. So option number three will not correct. So in it, heat addition takes place at constant temperature. So it's also wrong because we know that in Brayton cycle, the heat addition and rejection takes place at constant pressure. And pressure ratio is very important in idle Brayton cycle. Option fourth is also wrong. So if we go through the option, so A is having one only. So no, because one and two are both correct. B is third and fourth, wrong. C is one and two. It seems correct. And D 1, 2, 3, 4, it's wrong. So the correct option will be option number C. Okay. So the true statement for idle Brayton cycle is that it is commonly used as a topping cycle and its efficiency depends on the pressure ratio and types of gas used. Let's come to the question number 2. Supplementary firing in HRSG. It will be heat recovery steam generator. HRSG, heat recovery steam generator. We write the full form. Heat recovery steam generator. So what the supplementary firing in HRSG means. So we are having four options. So option A is means burning the residual fuel available in the exhaust of topping cycle, means burning additional fuel in the exhaust of topping cycle. It is not allowed in HRSG, and increase total power output. So we have to select which options are correct in the terms of HRSD. Okay, so take 2 minutes and try to answer. Try to think about that how heat recovery can used in heat generator, in steam generator, and what will be the output of supplementary firing. Try to recall class notes. Okay, let's start with the discussion. So as the name suggests, supplementary. Supplementary means we are firing some extra. Okay, supplementary. So the first option is means burning the residual fuel available in the exhaust or topping cycle. I think no, because we are not, because the most of fuel is already burned and residual fuel is not burned topping cycle. We are we will be supplementary firing for the in bottoming cycle. Okay, so we need supplementary firing so that in bottoming cycle there will be more heat available. So for this we will burn additional fuel in the exhaust of topping cycle, because the exhaust of the topping cycle is the input of the bottoming cycle. So at there we require the additional heat. So to get that additional heat, we have to burn a supplementary, we have to do the supplementary firing. Okay, so it seems that option A is incorrect and option B seems to be correct. Now let's come to the option C. So option C is it not allowed in HRSG? So supplementary firing is not allowed in HRSG? No, it is not the case, because we know that supplementary firing is allowed in the heat recovery steam generator, because it is essential if we want more power output. Because suppose if your topping cycle exhaust heat is not sufficient to run properly the bottoming cycle, so we need some supplementary firing. So it is allowed. And the supplementary firing in HRSG is increased total power output. So D seems also correct. So correct options are option B and option D. So supplementary firing in HRSG means burning additional fuel in exhaust of topping cycle and increase total power output. Okay, let's come to the question number 10. The question number 3 is for a gas turbine with maximum temperature T3 and minimum temperature T1. So we know that maximum temperature is T3 and minimum temperature is T1. The optimum pressure ratio for maximum net work output is given by. So you have to just draw a TS diagram and you have to try and you have to find out the formula. So let's take 2 to 3 minutes and try to answer. I think someone has joined the session. Are you able to see the slides and can you hear my voice?
Yes, sir. I'm able to hear your, able to
Okay,
listen your voice.
okay, so everything is coming. Okay, okay, fine. I think today only you and me. Maybe let's see. Because I think it's a rescheduled session, so maybe they forget to join. So try to solve this for a gas turbine with maximum temperature T3 and minimum temperature T1. The optimum pressure ratio for maximum network output is given. So let's see. So first of all, we should draw the TS diagram. Okay. So the TS diagram we can draw here. So you can see the TS diagram. Okay. So the process 1 to 2, 2 to 3, and 3 to 4, 4 to 1. So T1 is the minimum temperature and T3 is the maximum temperature. Now we have to find out the maximum work output. So let's see. So for idle Brayton cycle, the pressure ratio RP. Okay. So the pressure ratio RP is given by RP bracket to the power gamma minus 1 upon gamma is equals to T2 upon T1 equals to T3 upon T4. Okay. So the pressure ratio is RP to the power gamma minus 1 upon gamma is equals to T2 upon T1 equals to T3 upon T4. So the net work output, so W net. So net work output is W turbine minus W compressor. So here in Brayton cycle, the compressor is also having a good amount of work input because we are compressing the air. Okay. Earlier in steam turbine, uh, we were using pumps, so pump was not having so much amount of work. So for the ease of calculation, sometimes we have neglected that work, but in actual, in the gas turbines, we have to consider the compressor work also. So the net work will be W turbine minus W compression. So WT minus WC. So for WT, MA mass flow rate of air, CP specific heat, and T3 minus T4. So W turbine will be MA CP T3 minus T4 minus for compressor, it will be MA CP T2 minus T1. Okay. So this will be the formula for the net work output. Now we have given that we have to find the maximum network output. So for maximum, we can apply some conditions. For the maximum network output, the optimum pressure ratio can be found as the maximum temperature T3 and the minimum temperature T1 are fixed. Okay. So that we have fixed the T3 and T1. And now we have to write W net in terms of RP, T3 and T1. Okay. So we have to replace T2 and T4. Okay. So from using this pressure ratio formula, that is Rp to the power gamma minus 1 upon gamma equals to T2 upon T2 upon T1 equals to T3 upon T4. From here, you can find the value for T2 and T4, and you put the value of T2 and T4 in equation number 1. So we will get like this. W net will be equal to MACP T3 bracket 1 minus 1 upon Rp to the power gamma minus 1 upon gamma minus MACP T1 Rp to the power gamma minus 1 upon gamma minus 1. Okay. So after solving on difference, now, so I think you will get this equation. Now we have to find the maximum work output. So differentiate it. So on differentiation W net with respect to Rp. Okay. So because as mentioned that for optimum pressure ratio. So that's why we are differentiating it with respect to Rp. So dW net upon DRP equals to 0. So from the calculus, you know that when we want to calculate the maximum, so we can use the differentiation and make it equal to 0. So we will get the optimum value of that point. So the optimum pressure ratio will be, after differentiating it and solving, we will get this pressure ratio. So Rp optimum will be gamma T3 upon T1 the power gamma upon 2 gamma minus 1. So let's check the option. So option C is having the same term, T3 upon T1 to the power gamma upon 2 gamma minus 1. So the correct option will be option C. Okay. So for a gas turbine with maximum temperature and minimum temperature, the optimum pressure ratio for maximum network output is given by T3 upon T1 to the power gamma upon 2 gamma minus 1. This formula is very useful. Try to remember this because sometimes you will have direct numericals based on this formula. It's quite important. Okay, any doubt? Okay, let's come to question number 4. The efficiency of topping and bottoming cycle of a combined cycle power plant are eta1 and eta2 respectively. The correct expression of efficiency for combined cycle is for R. So maybe more than one options can be correct. Try to remember the class notes and try to answer this question. Take 2 minutes. Okay, let's start with the solution. So if you recall, then maybe you can remember the efficiency for a combined cycle can be represented as 1 minus eta equals to 1 minus eta 1 and 1 minus eta 2. Now we can simplify this term and we can check our options. So suppose if I transfer the eta to right side and the whole term on the left side to the right side. So I will get 1 minus eta 1, 1 minus eta 2 equals to eta. So this will be the efficiency of a combined cycle. So check the option so we can find option C is having similar term. So it's correct. Now again try to solve these two terms. Okay. Try to solve these two terms. So then we can find out. Let's see. So that eta will be 1 minus a larger bracket. I multiply this 1 to 1 and 1 to eta 2 and this eta 1 to 1 and again eta 1 to eta 2. So we will get 1 minus eta 2 minus eta 1 and plus eta 1 and eta 2. So again solve the bracket. Outside we are having minus sign. So if you have to change the signs of inside, it will be 1 minus 1 plus eta 2 plus eta 1 minus eta 1 eta 2. So this will cancel out. So that efficiency will be eta 1 plus eta 2 minus eta 1 and eta 2. You can check with the options. So we can find the similar term in option number B. That B is correct. So the correct options will be option B and C. So the efficiency of the topping and bottoming cycle of a combined cycle power plant that are having efficiencies of eta 1 and eta 2 can be represented as a single efficiency like that 1 minus eta 1 into 1 minus eta 2 and eta 1 plus eta 2 minus eta 1 eta 2. Option B and C are correct. Okay, let's come to the next question. Question number 5 is in a gas turbine, the atmospheric air is compressed to 6 atmosphere. So we are compressing the atmospheric air to 6 atmosphere. The maximum and the minimum cycle temperatures are 1200 Kelvin and 300 Kelvin. So T3 they have given, T1 they have given. Find the ratio of the gas turbine cycle efficiency to the Carnot cycle efficiency. We have to find out the gas turbine efficiency. We have to find out the ratio of gas turbine efficiency and the Carnot cycle efficiency. So I think you can easily calculate the Carnot efficiency because you know the maximum temperature and the minimum temperature. Now the ambient is at 1 atmosphere and 300 Kelvin. So you have given the ambient condition also. Gamma is also given. So now you have to find out the gas turbine efficiency and the Carnot efficiency. Then you have to find out the ratio. So take 3 minutes to solve this question and then we will discuss. Try to recall the formulas. Then I think you will be able to answer it. Okay, so let's start with the solution. Okay, so as we can see that we know that Carnot efficiency is the Carnot efficiency is 1 minus T min upon T max. Okay, so we have given the T minimum temperature and the maximum temperature. So the Carnot efficiency will be 1 minus T minimum is 300. We have given in the question, and the T max is 1200. So 1 minus 300 upon 1200. So you will get 0.754. You can say 75%. Okay. So this will be the Carnot efficiency. Now the Brayton cycle efficiency will be, as we have also know the formula. The formula is 1 minus 1 upon Rp to the power gamma minus 1 upon gamma, where Rp is the compression ratio. Okay. So the Rp will be P2 upon P1. So we have given the maximum pressure is 6 atmosphere from the ambient to 1 atmosphere. So Rp will be P2 upon P1, 6 atm upon 1 atm, it will be 6. Okay. So now put the value of Rp and gamma in this Brayton cycle efficiency formula. You will get the efficiency of Brayton cycle is equals to 1 minus 1 upon 6 to the power gamma minus 1 upon gamma. After solving, you will get 0.40066. So the question has asked about what is the ratio of Brayton cycle and Carnot cycle efficiency. So now we know the efficiency of Brayton cycle and also know the efficiency of Carnot cycle, so that you can easily find out the ratio. So the ratio will be 0.40066 upon 0.75. So after solving, it will come to 0.5342, which is equal to 0.5. So the correct answer is option B. Okay. So basically, try to remember this formula, because every time it will be difficult to derivate these formulas. Okay. So try to you have to understand it and try to remember this. It will be easy for you to solve the numericals then. Any doubt? Okay. Let's come to the next question. Okay. So the next question is the given below block diagram of a gas turbine, gas power plant, shown combustion chamber, intercooler, reheater, and regenerator. So it's quite a complex diagram. So maybe more than one or two, more than one question will be connected to this numerical problem. Okay. So try to read it carefully and try to understand it. So which are represented by the letters P, Q, R, and S. So we have given like combustion chamber, intercooler, reheater, and regenerator, which are represented by letters P, Q, R, and S. Identify the correct options showing the correct representation of above mentioned components. So you have mentioned, you have given a schematic. In schematic, we have given like P, Q, R, and S. So now you have to find out the correct identification of these P, Q, R, and S. Okay. So the options A, B, C, and D you can see. So maybe the P can be reheater, P can be intercooler, P can be combustion chamber, P can be regenerator. So go through all the options, try to recall the class notes and answer it. Just take 2 minutes. try to remember the like basics, like if we are using the compressor, two compressor, okay, and between two compressors we have to put something so that we don't have to use more work, okay, because we know that compressing a gas at high temperature require more work as compared to compressing it at lower temperature. So P should be what? Okay, so let's start with the solution. So as I already told you that the compression of a high temperature gas require more work than compression of a low temperature gas. So we try to avoid the more work. So what we can do? So we can cool the gas from first compressor so that at the second compressor's inlet, the gas temperature will be not so high. So this P should be an intercooler. It should be an intercooler. Okay. So the outlet of compressor 1 is going through the intercooler, and the intercooler the gas temperature will reduce, and then we are again compressing it. So at less amount of work input we can get a more pressure ratio. So the P will be intercooler. Okay, after intercooler the gas is going through the Q. So in Q you can see that Q is having two streams. One stream is inlet and the other stream is outlet. Okay, so it's like a heat exchanger or regenerator. So the Q will be regenerated because the exhaust stream from turbine is going through the Q, and the exhaust and the outlet stream of compressor is also going through the Q. So this exhaust stream will be at high temperature as compared to this inlet stream. So what is happening here? So this exhaust stream at high temperature is giving heat to the this incoming stream from the compressor. Okay, so this Q will be regenerator. After Q you can see the gas stream is going to the section R. So here R, the combustion will happen. Okay, and the net and the total heat addition will be happening here. So R will be the combustion chamber. So here the temperature will increase and the steam will go into the superheated state. After that the air will be going to at very high temperature, and after that that will go to the turbine. So from R it is going to turbine, in turbine it's going to the this S. Okay, and after S again going to the turbine. Okay, so here we are using a reheater. In our previous class also we have discussed it that by using reheater we can use two turbines, high pressure turbine and low pressure turbine. Okay, and we can get more work output at less input. Okay, so S will be reheater. So the correct option, so the P will be intercooler, Q will be regenerator, R will be the combustion chamber, and the S will be reheater. Now check the options. So our all conditions are matching with option B. So the correct answer will be option B. Okay, any doubt? Okay, let's go to the next question. So by using a combined cycle gas turbine or GT system and steam power plant SPP system, so we have given four options. You have to find out the sorry, you have to find out the correct one. Okay. Option A is specific fuel consumption can be decreased, efficiency can be increased, work output can be increased. The waste heat from the gas turbine is routed to a steam turbine which generate extra power. So go through all the options and let me know. Take 2-3 minutes. Question is that by using a combined cycle and steam power plant, we have to identify the correct statements. So what can be the, like, what about the efficiency? What about the work output? Try to go through all the options. Okay. So if we are using a combined cycle, so our main purpose to use a combined cycle system is that so that we can use the waste heat of topping cycle in bottoming cycle to increase the work output. Okay. So the first option that will come into our mind will be the that if we are using a combined cycle system, then the work output will be increased for sure. So in the options, you can see the option C. Work output can be increased. So this will be correct. So suppose when you are increasing the work output at the same input, then what will happen? Because we know that efficiency is output upon input. So we are increasing the work output at the same rate of input. Automatically the efficiency will be increased. So option B will be also correct. Now come to the option D. The waste heat from the gas turbine or topping cycle is routed to the steam turbine bottoming cycle which generate extra power. Yeah, it's correct. That's how we are doing it. So in combined cycle, we are using the exhaust heat or you can say the waste heat of a topping cycle in the bottoming cycle. So D is also correct. And option A, specific fuel consumption can be decreased. Yeah, because you are increasing the more work output, so that in that way, the specific fuel consumption for the work output will be decreased. Option A is also correct. So let's see the answer. So option A, B, C, and D all are correct. So by using a combined cycle, we can do all these four things. Let's come to the next question. A simple idle Brayton cycle with air as the working fluid. So we have given air as the working fluid, okay? Has a pressure ratio of 11. The air enters the compressor at 300 Kelvin and the turbine at 1500 Kelvin. And gamma is equals to 1.4. The bake work ratio in percentage will be. So you have to find out the bake work ratio, okay? So take 2 minutes to 3 minutes and try to answer this question. Just try to recall the basics of a Brayton cycle. Just make a basic schematic and mark all the points 1, 2, 3, and 4, and try to put this value. And after that, maybe you will be able to calculate it. Yeah. So try to solve this. Do we have any answer? Okay. So first of all, whenever you have a problem based on a cycle, okay, based on any cycle like Brayton cycle, Rankine cycle, any cycle, the best thing to start the solution is with a basic schematic of TS diagram or HS diagram. Okay. So here we can draw a TS diagram. So we have to mark the points 1, 2, 3, and 4. In this way, you can see 1, 2, 3, and 4. Okay. So now we have given that working fluid has a pressure ratio of 11. So that we have given the RP. RP is given as 11. Okay, so RP is 11. Okay. So the RP will be that T2 upon T1. Okay. You know the T2 upon T1 will be RP to the power gamma minus 1 upon gamma. Okay. And we have given gamma as 1.4, RP as 11. So put the value of RP and gamma, you will get T2 upon T1 equals to RP to the power gamma minus 1 upon gamma equals to 1.9839. Okay. Now the P2 equals to P3. We know that heat addition takes place at constant pressure, and P1 equals to P4 because heat rejection is also at constant pressure. So that P2 equals to P3 and P1 equals to P4. Now put the value of this. So, okay. So we have also given T1. I think T1 is given. The air enters the compressor at 300 Kelvin. So we have given T1. T1 will equals to 300 Kelvin. And we know that T2 upon T1 equals to 1.9839. So from here, T2 will be multiply this T1 to this term. So T2 will be 595.198 Kelvin. Okay, now we have T2 and okay, and T4 will be, because we also know that T3 upon T4 is also equals to RP to the power gamma minus 1 upon gamma. We have given the T3 as 1500 Kelvin. Okay, we know this value 1.939. Put all these value, we will find the T4. T4 will be 756.08 Kelvin. Now you know the T3, you know T4, you know T2, you know T1. So what is the bake work ratio? So bake work ratio is the ratio of compressor work to the turbine work. So compressor work here will be H2 minus H1 and the turbine work will be H3 minus H4. So that we are using the air. So H2 will be CPT2, H1 will be CPT1. To put all the values, so the formula will become CPT2 minus T1 upon CPT3 minus T4 equals to 0.3968, or you can say 0.40 or 40%. Now see the option. So option A will be correct. So the bake work ratio is 40%. Okay. The bake work ratio is ratio of the compressor work to the turbine work. I think it's clear to everyone. Any doubt? Okay. That comes to the question number 9. So question number 9 is in an ideal Brayton cycle with perfect intercooling. So we are doing the perfect intercooling. T3 equals to T1 and T2 equals to T2 dash equals to T4. Air steadily enters the first compressor. The first compressor of the gas turbine shown in figure below 800 kilopascal. So the figure is shown here. Okay. The pressure ratio across the two-stage compressor is 8. The intercooler operates at an intermediate pressure so that compression work is minimum. One may assume ideal gas behavior, so the delta H will be Cp delta T. The ratio of work done by the compressor in two-stage compression, first stage 1 to 2 days and second stage 3 to 4. With intercooling to the work done by the compressor in single stage compression process 1 to 2 in percentage is. So read the question carefully and try to answer. Take it's quite a big question. Take 3 minutes. First of all, you should see the diagram very carefully. You should read the question carefully. After that, you should start the solution. Okay, so let's start with the solution. So again, let's go through the diagram first. Okay, so you can see we have given that an ideal Brayton cycle with perfect intercooling. So T3 equals to T1. So you can see that perfect intercooling is T3. Let me mark my pointer. Okay, so you can see that this T3 is equals to T1. Okay, so because we are using the perfect intercooling, and the T2 dash, this T2 dash is equals to T4. This T2 is equals to T4. So this is the perfect intercooling. Okay, so first we are compressing it from 1 to 2 days, then intercooling 2 days to 3, then again 3 to 4. Okay, the pressure ratio across the two-stage compression is 8. The pressure ratio is given is 8. The intercooler operates at intermediate pressure so that the compression work is minimum. So the intercooler is operating at the intermediate pressure, means 4. Because the pressure ratio total is 8, so it is operating at 4. Or one may assume ideal gas behavior. The ratio of work done by the compressor in two-stage compression. First stage 1 to 2 days, this 1 to 2 days, and second is 3 to 4. So with intercooling to the work done by compressor in single stage compression in percentage is. So using given pressure ratio and properties of isentropic process 1 to 2 days as mentioned in the question, intermediate pressure is given as, so P2 dash is will be, it's not directly 4. Okay, it is not directly 4. I told you just by mistake wrongly. Okay, so the correct the correct formula for the intermediate pressure is P2 dash is root square root of P1 dot P2, okay, dot RP. So after solving this, we have given the P2 as 800 kilopascal. Okay, so the P2 will be 800 kilopascal and P2 dash will be 100 into 800 equals to 282.84 kilopascal. Let me shift to my, okay. So P2 also we have given that P2 dash equals to P3. Okay, for process 1 to 2 days. So this P2 dash is also equals to P3. So now T4 upon T3 will be P4 upon P3 to the power gamma minus 1 upon gamma. So T4 will be, multiply this T3 to right side, T3 into 800, we know P4, we know P3, we know gamma. So this value will come. Now T4 dash equals to T2 dash. Okay, so now using the relevant values, we calculate the compressor work with intercooling. So first stage is process 1 to 2 days. So the process 1 to 2 days will be the first stage, and second stage is process 3 to 4. So the work compressor with intercooling will be the first stage work plus the second stage work. So H2 dash minus H1 plus H4 minus H3. So it will be Cp T2 dash minus T1 plus Cp T4 minus T3. So we are going from T2 dash minus T1 and T4 minus T3. And the compressor without intercooling will be H2 minus H1. So without intercooling, we are going like H2 minus H1 directly from here to here. Okay. So H2 minus H1. So now you know all the values of T1, T2, T3, T4, everything. So put all the values, you will know the answer. So it will be 0.8524 or 85.24% or 85%. So the correct option will be option A, 85%. Okay. So basically, whenever you're trying to solve this type of questions, try to find out the values of the points which are required. Okay. So in this case, we require the points for the compressors because we need to know the ratio of compressor work with intercooling and without intercooling. So after that, we can solve it. Okay. Now let's comes to the next question. So the gas turbine section of a combined gas steam power plant has a pressure ratio of 15. Air enters the compressor at 300 Kelvin and 1 atmosphere at rate of 13 kg per second is heated to 1500 Kelvin in the combustion chamber. The combustion gas leaving the gas turbine are used to heat the steam made to 400 degree at 10 megapascal in heat exchanger. The combustion gases leave the heat exchanger at 420 Kelvin. The steam leaving the turbine is condensed at 15 kilopascal. So the figure is given here. The table are given in the discussion, the next page. So first, you should see the figure correctly. Okay. So from here you can see the air input, air in. It's going to the compressor. From compressor, it's coming out at point 2, state 2. From state 2, it's going to the combustion chamber. Coming around state 3. At state 3, it's going to the gas turbine. And at gas turbine, it's coming out as state 4. From state 4, it's going in a heat exchanger where it's exchanging heat to the bottoming cycle. In bottoming cycle, it's giving to the heat for the steam generation. The steam is generating in state 6. The generated steam is going to the steam turbine, then condenser, then pump, and then again this way. So this is a topping cycle. And this is a bottoming cycle. Okay, now try to find the question numerical. So we have given state P1, T1, P2, P1, T1, H. Okay, enthalpy have given it state 1, 2, 3, 4, 5, 6, 7, 8. And you're also given like P1 and T1, P2, S2 equals to S1. We have given so much of data. So assuming all compression and expansion process to be isentropic, the mass flow rate ms of steam will be. We have to find out the mass flow rate. So let's take just take 2 minutes, 1 to 2 minutes to read the question and understand the TS diagram carefully. After that, I will show you again the table and you should solve the question. Okay. First of all, you have to understand the topping and bottoming cycle and try to understand the TS diagram.
Sir, one doubt, sir.
Yeah.
Sir, in topping cycle, in the TS diagram, it is mentioned means 1, 2, 3, 4, 5, and 1. My question is, sir, doubt is when the air from 4 to 5 is cooled in heat exchanger, and then same air will go to compressor at the point 1.
Okay.
So 5 and 1 will be means in same means 5. Then after 5, how can it cool to 1? Means that is a question, sir.
Okay. Actually, if you see in this diagram, so this 5 and 1 is not connected. Okay. So maybe the
Yes.
5 will be exhaust. Okay.
Okay,
And
okay.
1 is again the fresh
Fresh air,
air.
no? Okay, that is good.
Okay. Because it's not connected. It's not the topping cycle is not connected thoroughly. Okay. So
Ye-
maybe some cooling is in between happening, or maybe some pressure is also entering.
Yes,
That's why the 1 is lower than the 5.
yes.
Okay. So these are the data for state points. So it's quite a long question. Okay, so let's start the solution. So we have to find out the mass flow rate. Okay, so the mass flow rate for steam is, so that energy balance on the adiabatic heat exchanger. So we should apply the energy balance on adiabatic heat exchanger. So it will be mass flow rate of air H4 minus H5, and mass flow rate of steam H6 minus H9. Let's go back. So basically we are applying the energy balance to this heat exchanger. Okay. So it will be mass flow rate of air H4 minus H5, and mass flow rate of steam H6 minus H9. So using the relevant values in question, so mass flow rate of steam will be mass flow rate of air H4 minus H5 upon H6 minus H9. We have given the enthalpy values, put the values, and you will know the answer. So the answer will be, so 1.2407 kg per second. So see the option. So option C, 1.2407 kg per second. And one important thing is that remember in which unit they have asked the answer. Okay. So here they have clearly mentioned kg per second. Okay. So the unit is very important, because you can see it's 1.24, 12.4, 124, 0.124. So if you missed any multiplication of 10, 100 or 1000, like kg, grams and milligrams, maybe you will get wrong answer. So try to always remember the unit in which they have asked and the units which you are having. Okay. So always try to sync in same units. So the correct option will be using the basic energy balance of adiabatic heat exchanger, because it's adiabatic, so there is no loss of heat. So the heat from the high temperature steam is directly go to the water to generate the steam. In this way, we can find out the mass flow rate of steam. So the next question is, as per the information given in question number in 10 or previous question, the net power output considering pump work. So now you have to find out the power output. So let me again show you the diagram. I tried to formulate the formulas which will be used for the power output, and then I will show you the enthalpy values and then try to find the answer. It'll just take 2 minutes.
Sir, sir, can you
Yeah,
back the slide? The answer, sir. The
this
answer,
one.
sir. Mass flow rate for which is calculated steam for steam.
Okay. Let me. Yeah, yeah. So mass flow rate of steam is 1.2407.
Sir, the one doubt, sir, actually, when we apply this equation, that energy equation for this heat exchanger, uh,
Mm-hmm.
is if suppose, for example, if in the process, if suppose this flow for steam or this second cycle, that is bottoming cycle, if suppose by mistake or by some intentionally flow rate is reduced, for example, so whether the enthalpy is remain constant or it will be go on increasing.
Okay. Actually, I'm not getting you. Please again repeat the question.
Now, actually, it is already value is fixed, means the pressure, temperature, and enthalpy
Okay.
is okay because
Okay.
pressure, temperature is fixed for the topping or bottoming cycle, and then
Mm-hmm.
we are getting the mass flow rate for steam or for air. Okay, but sir, question is suppose because this topping cycle is fixed and we are uh, getting that waste heat recovery from in endorsing or applying this or installing bottoming cycle, right, sir?
Right.
So question is, sir, suppose when after installing the bottoming cycle, suppose the mass flow rate for this water, steam and water, right? If reduce for any reason, for example, so
Okay.
whether
Yeah.
this steam this side, that is the enthalpy side, na H6 H9 what if the if is it go increasing or will remain fixed or how, sir?
No, no, it will change actually. Yeah, it will change because you know that actually, if you're only, uh, you can see that the enthalpy are depending on the state points, state properties. Okay, so it's depending on the temperature and the
Pressure.
pressure. Okay, so if your temperature is not fixed, so suppose on for a particular temperature, for particular pressure, we are having enthalpies and we are having this heat balance. Okay, so after that we are getting this value. So if we are having this value of steam, okay, so whenever we are installing a bottoming cycle, then first of all we have to consider all the state points. From all the state points we will apply the energy balance and then we will know the mass flow rate of steam. Now we will ensure that our bottoming cycle will have this steam, okay, so that the other parameter will be as per our calculation. Now suppose in case you now if you increase the mass flow rate of steam, okay, now if you increase the mass flow rate of steam, then what will happen? If you increase the mass
Uh,
flow rate of steam, now just try to think what will happen here.
if no, sir, mass flow rate if it increase, then enthalpy obviously is goes on increasing. If it reduce, then it will increase. But sir,
Enthalpy will increase
no, no,
if you increase the mass flow.
no, no, if
No,
it decrease, then increase. It's inversely, na.
sorry.
Mass flow rate if the steam for steam if it is
Okay.
reduced. I'm I'm sir. My question is for bottoming cycle.
Yeah, I'm
On
I'm
a
talking
top.
about bottoming cycle only. I'm talking about bottoming cycle only. Let understand it. Suppose in bottoming cycle we have find out the temperature and pressure and based on that enthalpy. Okay, and we have find out the a standard steam flow rate. This one. Now,
Yes, sir.
if you are saying that in bottoming cycle, if we increase the steam flow rate, okay, just
Okay, increase in
uh, so we are increasing the steam flow rate, but we cannot change thermodynamics of the heat exchanger. Okay, so heat exchanger is going to work in the same way. Okay, so
okay,
now apply
okay,
your concept to this equation, this
sir.
heat balance equation. Now suppose
Yes,
in this equation, if you increase the ms value, then what will happen
yes.
to this value h6 minus h9? It will increase or decrease
Will
or remain same?
will decrease, sir.
Yeah, so that if you are increasing the steam quantity, then enthalpy will decrease
Dec-
because we know that the this because this air because this quantity m air h4 minus h5, okay, it will remain same. for topping cycle.
sir.
So for this to remain same, if you are increasing the steam, then your state point will decrease. And if your state point will decrease, then it will affect your the work output
Pressure temperature.
because your enthalpy is decreasing. In easy way, you can understand that if you are increasing the so much of quantity of the steam, okay, so much quantity of water, okay, so basically you are dissipating the heat. If you're dissipating the heat, then
Yes, sir.
temperature will reduce, and the temperature will reduce, and enthalpy will reduce. If you're supplying less amount of steam, then what
More.
will happen? So that enthalpy will
Mm,
increase very high. Okay,
yes, sir.
enthalpy
Yes,
will
sir.
increase. Now, if enthalpy will reach beyond some points, then maybe it can affect the other thermodynamics. Okay, so we have to make a balance. So whenever we want to install a thermodynamic plant or power plant, first we will do all thermodynamic calculation. Okay, basic calculation on standard method with standard methods. After that, we apply it. I think your doubt is clear.
Doubt is there, sir. One just little bit doubt.
Yeah.
If mass flow rate, suppose mass flow rate is increased on bottoming cycle, then
Okay.
delta H, that is it will reduce. If it increase, then it will reduce. But sir,
Yeah.
is it affect? It will affect on that's temperature pressure, na sir? Means that
Yeah. Yeah. It's affecting. Yeah. Yeah. It's affecting.
um,
That's why enthalpy is decreasing.
so means that it will work, sir. Actually, the point is only design point. Suppose the already is designed for that is a heat exchanger and that condenser is designed for particular pressure, temperature, and constant mass flow rate. Suddenly, my mass
Okay.
flow rate is decreased or increased, then it will affect on the thermodynamic pressure and temperature. So it will remain the same design. Can be means that. Pressure and temperature will sustain for that equipment, that compressor,
Yeah.
condenser,
Yeah.
that is
Actually, for practical viewpoint, as I know that whenever we are designing a system, then we always take a tolerance. Okay. We always take a range. Okay.
yes, yes. Okay,
And
okay.
suppose some equipments are very sensitive to some particular range. If the flow rate or if any parameter is beyond that range, maybe that equipment may fail. Then we have to ensure that that equipment will always get the desired range.
Yes, yes, yes.
Okay, so
Got it, sir.
whenever your designer is designing the power plant system, so he will decide what is the bottoming cycle, how is his system is efficiency and all. So based on that, he will design it, and maybe he will know that if the flow rate of steam slightly increase, slightly decrease, or maybe at the optimum point, so there will be a small difference in the work output, or maybe there will be small difference in the equipments. Then there will be no issue. If suppose if you are increasing the flow rate and the totally your system is going to failure, then the designer will always install a system that ensure the required flow rate. That is
Sir, sir.
the point of this calculation. That is the reason we are doing this calculation, so that we know this is the optimum flow rate, and if we increasing, then this will happen, and we decrease, so this enthalpy will change, and this thing can happen. So in that way, we will decide that this range is the optimum, this range is the required range, so we will always operate our system on this range. Okay.
Thank you.
Okay. Thank you. So now, as per the information given in the question 10, the net work output considering pump work. So for work output of the network output, so the network output will be the output from turbine 1, output from turbine 2, minus compressor work, minus pump work. So see the diagram again. We are having a gas turbine, a compressor, a steam turbine, condenser and pump. So the output work is coming from gas turbine and steam turbine, and the input work is going to the compressor and pump. So basically, we have to know the enthalpies of H3, H4, H2, H1, H6, H7, H8, H9, and the flow rate of steam and air. Now we have already know the flow rate of air. We have already know the flow rate of steam. We have given the enthalpies. So put all the data. You will get the answer. Okay. So W net will be mass flow rate of air into H3 minus H4 plus mass flow rate of steam H6 minus H7 minus mass flow rate of air H2 minus H1 minus MS mass flow rate of steam H3 H9 minus H8 equals to 7.3082 megawatt. So correct option is option B. So on the basis of the details provided in question 10, the thermal efficiency of combined cycle by rounding decimal to the nearest whole number. So for this
Sir,
question only,
the question once again.
yeah, this one,
Yes, sir. Okay, sir.
okay. So in next question, we have to find out the combined cycle efficiency. So I think we have calculated the work output of turbine, we have work output of compressor and all mass flow rates. So the combined cycle efficiency will be the thermal efficiency of combined cycle. Okay. To obtain the thermal efficiency, the external heat addition is evaluated. So we know the work output. Okay. Now we have to know the heat addition. So heat addition will be in combustion chamber. So we should know the mass flow rate of air and H3 and H2, enthalpies of H3 and H2. From this data, we can know the value. So you can see we have given the enthalpy of H3 and H2. So from here, we can calculate the value. So Q input will be mass flow rate of air, H3 minus H2. So it will be 11.0896 megawatt. So one point is also whenever we are dealing in megawatt, then try to consider the decimal up to 4 to 5. Okay. And the thermal efficiency of the combined cycle will be W net output and Q input. So this net output work is always this net output is considering the turbine work. Okay. Both turbine, the gas turbine and steam turbine work, and also considering the pump work and the compressor work. So we know the net work output, we know the net heat input. So that the thermal efficiency of combined cycle will be W net upon Q in. It will be 0.6590 or 0.66% or 66%. I think it's clear to everyone. Okay. So question number 13 is the efficiency of HRSG can be improved using. HRSG is, anyone know the full form of HRSG? So HRSG is heat recovery steam generator. Try to recall the class notes and answer the question. Take 2-3 minutes, 2 minutes. Anyone? Okay. So it's HRSG, heat recovery steam generator. So we have to improve it. Then we can do it by multiple pressure steam generation. Okay. So if you refer the class notes, maybe you can more understand about it. So multiple pressure steam generation. If you are generating steam at multiple pressures, so we can improve the efficiency of HRSG. Low pinch point temperature difference. If the low pinch point temperature difference is there, that means that we are maximizing the heat transfer from the exhaust of topping cycle. Low approach point difference. Low approach point difference means that you have to provide a very little bit of subcooling. Okay. And high pinch point temperature difference is wrong because we try to achieve the low pinch point temperature difference. Option A, B, and C are correct. For more detail, you can refer the I think week 4 last class. I think in that the professor has talked about in detail in HRSG. Okay. So the HRSG efficiency can be improved using multiple pressure steam generation, low pinch point temperature difference, and low approach point temperature difference. Okay. Question number 14 is which of the following statements are correct for the use of regeneration, intercooling, and reheating in a gas turbine cycle with a given inlet conditions, pressure ratio, and maximum cycle temperature. Try to go through all the points and discuss the answer. Take 2 minutes. Okay. So the correct options are A and D. So A is using regeneration with no reheating or intercooling. So we are only doing the regeneration, not applying any reheating or intercooling. In gas turbine cycle, W net output is WT minus WC remains unchanged, whereas the efficiency of the cycle increases. Okay, anyone want to discuss it? So basically, in regeneration, what we are doing, we are decreasing the heat input. Okay, because we are utilizing the exhaust heat to preheat the stream that is going to the combustor. Okay, so in that way we are decreasing the heat required in the combustion chamber. So basically, it is not affecting the work output. So W net will remain same. WT, WC remain same. We are just decreasing the heat input. So if we know that the efficiency is output upon input. If you are decreasing the heat input, the efficiency will increase. So option A is correct. Option B, by staging the compression process with perfect intercooling, with no regeneration and reheating, the heat input to the cycle decreases, but the compression work decreases. So we are not applying the regeneration and reheating. So we know that the heat input to cycle will not decrease. If we are applying the regeneration, then there is chances of decrease of the heat input. Okay. If you are applying the perfect intercooling, it means that the work input to the compressor is decreasing. The heat input is not decreasing. So option B is incorrect. Now the option C is by staging the heat supply process with a combustor and reheater. So we are applying by staging the heat supply process with a combustor and a reheater with no regeneration. We are not applying regeneration and intercooling. The cycle efficiency always increase? No. Because for efficiency to increase, regeneration should be there, or you can also prove it by the calculations. Okay. The D is to improve the efficiency of the cycle. Intercooling and reheat are always used with regeneration. That's correct. So regeneration is always required if we want to improve the cycle efficiency with intercooling and reheat, because regeneration is reducing the heat input, and heat input is a deciding factor in the efficiency. In that way, option A and option D are correct. Okay. Number 15. Many of the HRSG has a selective catalytic reactor to remove NOx. Which of following is used as the reducing agent? Try to recall it. So the correct option is option B. Aqueous ammonia. Aqueous ammonia is used in the HRSG selective catalytic reactor to remove the NOx. Now come to the question number next. What is the advantage of a combined cycle power plant? So option A is fuel flexibility, high availability, high thermal efficiency, and all of the above. Take 1 minute to answer.
All in the above, sir.
Yeah, because if we are using a combined cycle power plant, then there is a fuel flexibility, there is high availability, and high thermal efficiency. Identify the probable topping cycle and bottoming cycle for a combined cycle power plant where SPP steam power plant, TE thermoelectric power plant, and TI thermoionic power generation. You have to combine in like topping plus bottoming cycle. So which cycle can be a topping cycle and which cycle can be a bottoming cycle? Go through all the option and you will know the answer.
Option C, sir.
Option C. Try to rethink, because you are saying that steam power plant plus the thermoelectric power, TI. Okay. The correct option is option A. Okay, because we always try to make the steam power plant as a bottoming cycle because it is easy to generate the steam from exhaust heat. Okay, that's why we are using the steam power plant as a bottoming cycle and all other cycle as a topping cycle. Because if we are having exhaust heat, so it is easy to generate the steam. Okay. And also the Rankine cycle, for the steam turbine, the other pressure and temperature are also favorable in bottoming cycle, not in the topping cycle. The efficiency of a gas turbine is so the answer is option D. Yeah.
D.
So it is ratio of 1 minus 1 upon Rp to the power gamma minus 1 upon gamma. So gamma here we are taking as a K plus ratio of specific heat at constant pressure and constant volume, and P2 upon P1 is the pressure ratio. So it will be 1 minus 1 upon P2 upon P1 to the power K minus 1 upon K. Which one is the true for ideal Brayton cycle? It is commonly used as a topping cycle. Its efficiency depends on the pressure ratio and types of gas used. It is used as a bottoming cycle. In it, heat addition takes place at constant temperature.
C, sir. Option C.
Option C. Yeah, correct. Because it is commonly used as a topping cycle and it depends on pressure ratio and type of gas used. Because in the last question also, Rp, so P2 upon P1, it is depending on the pressure ratio and gamma, which is the specific ratio of specific heat. So specific heat is depend on the gas type. Okay. So basically, its efficiency
Sir,
depends on the pressure
it
ratio
may
and types of gas used.
option 4B may be that is the in a heat addition take place in constant pressure as a constant constant
No, it's because
pressure
in
of the
heat addition, in Brayton cycle, heat addition is taken place at constant pressure, not constant temperature. Okay. And the third is it is used as a bottoming cycle. No, because we are using the Brayton cycle as a topping cycle. So 3 and 4th are wrong. Okay.
Yes, sir.
Okay. Identify the correct TS diagram for an ideal Brayton cycle. Correct TS diagram for ideal Brayton cycle.
Option B, sir.
Option B.
E, sir.
Okay. Yeah, correct. Option B is correct.
Option
Yeah, because we know that the compression and the expansion is the isentropic and the heat addition and the heat rejection is constant pressure process. So both conditions are uh, matching with the option B. The difference in the temperature of the exit of a economizer and the inlet of evaporator is known as its approach. Okay. The difference in temperature of the exit of the economizer and the inlet of evaporator. Because in economizer, the water is normally try to exit at a saturation condition, but sometimes it is not saturated, it's just below saturation. Okay, and in evaporator, the water phase is completely converted into the vapor into the vapor phase. Okay, so that the temperature difference between the economizer and the inlet of the evaporator is known as approach. The performance of heat recovery steam generator can be improved by if we want to improve the heat recovery steam generator.
B, sir, using low pitch point.
Yeah, correct. So if the pinch point is low, it means that the maximum amount of heat is transferred to the cold stream. Okay, so we can do the maximum heat recovery. Why selective catalytic reactor is used in HRSG?
To remove NOx.
Yeah, correct. So to remove the NOx, we use the selective catalytic reactor in heat recovery steam generators. The efficiency of Brayton cycle is enhanced by, so it can be enhanced by intercooling and by increasing the
Increasing the
pressure ratio. Okay. So if you compare if you know the efficiency formula, it will be 1 minus 1 upon Rp to the power gamma minus 1 upon gamma. So if you compare the values, then you will know that the option B and D are wrong. Why there should be a difference in temperature of the exit of the economizer and inlet of evaporator?
To remove NOx.
Sorry.
Option A, sir.
Option A, to avoid boiling in evaporator. Try to take 1 more minute and try to answer it. Okay. So the correct option is option B, to avoid boiling in economizer. So we try to make any difference between the evaporator temperature and the economizer to avoid boiling in economizer. Okay. So basically in economizer we try to increase the temperature of the water near to the saturation point. Okay, not up to the saturation. There will be small difference. That will be the temperature of approach that will be covered in the evaporator. Okay, so basically the economizer will handle only the liquid part, liquid water, not in the gas form.
Option B,
Due
sir.
to, yeah, so option B is correct. Efficiency of the combined cycle power plant is,
C. Options.
yeah, so efficiency of combined cycle power plant is eta equals to eta 1 plus eta 2 minus eta 1 eta 2.
Option B.
No, it's option C.
Option B, sir.
Option
To
C,
avoid
option C.
boiling economizer.
Yeah. That question is already solved. Yeah. So now we are at this question. Efficiency of the combined cycle power plant. It will be efficiency of eta equals to eta 1 plus efficiency of 1, then the bottoming cycle efficiency 2 minus eta 1 eta 2. So in a gas turbine, the atmospheric air is compressed to 6 atmosphere. The maximum and minimum cycle temperature you have given. Find the ratio of the gas turbine cycle efficiency and the Carnot cycle efficiency.
Sir, we already did solve this problem.
Yeah, I think we have covered in our previous. Yeah, okay. Okay, maybe these you can try at your home. Okay. The efficiency of the topping and bottoming cycle of a combined cycle power plant are given 0.4 and 0.3. So the efficiency of the combined cycle will be. Yeah, please tell me the answer.
8%, sir.
Okay, so it's 0.4 plus 0.3 minus.
B, sir. B.
Yeah, 0.4 into 0.3. Okay. In arrangement described below. Okay. I think the question is incomplete. Okay. Yeah. The figure shown shows below the block diagram of a gas turbine power plant. Identify the correct matches. Go through all the options and tell me the answer.
Option B, sir.
Option B. Okay, option B means 2 only. Okay, so you are saying R is the combustion chamber only. Okay, yeah, because then what will be the P?
Intercooling, sir.
P will be intercooling because between the compressor we are putting an intercooler so that the outlet gas from the compressor 1 will be intercooled to a lower temperature so that it will require less work in compressor 2. Okay, then what will be the Q?
Economizer, sir.
Q, regeneration. Regeneration.
Yeah, Q will be regeneration, so that we are using the exhaust heat from the exhaust gases from the turbine to preheat the gas input to the combustion chamber. And R is the combustion chamber, then what will be the S?
Reheater, sir. Reheater.
Yeah, S will be the reheater. So the correct option is option B.
Sir, 1 minute, sir.
Yeah.
Sir, here actually 2 is correct, but sir, if we think on a Q, can we consider Q as a afterburner? Not logical, but if we consider in the path that is going from 6 to, I think it is 4 to 5, for that Q can be considered the afterburner if Means it's a burning now. It's actually
No,
heating.
no. It's not burning. If you are burning
heating.
something,
Okay,
yeah,
okay, that is the logic. Okay, it is heating only,
yeah,
just heating.
yeah.
Okay,
Afterburner, you can say afterburner is similar to combustion chamber. Okay, so afterburner
okay,
is
but
basically a
it was
combustion chamber.
okay. It involves fuels and all that, na? Okay,
Yeah, yeah, yeah. So if
okay.
the Q will be afterburner, then there will be only one stream to the Q. But you can see there are two streams. One stream is input and the other stream is output. So if the two stream are involving, then that cannot be an afterburner. That will be like an
Okay,
heat exchanger, so regeneration.
okay, sir. Okay, thank you.
Okay, okay. So I think it's enough for today's class.
Sir, one more
So
question. Next question, sir. Next question. Sir, next question. This one, sir.
yeah. So in a gas turbine or combined cycle, the ratio of mass flow rate of water is 0.25. The enthalpy gained by the water is 500 kilojoule. If gas enter into HRSG with the enthalpy of 650, what is the enthalpy of outgoing gas? So it is your homework. Okay. So you can try this question at your home. I think
Sir,
we have
tell
solved.
me the answer. I will
Answer will
solve.
be option A, 525 kilojoule per kg.
Okay, sir.
Okay. So I think many of you have joined very late today. So were you aware about the class or not? Everyone, were you aware about the class? Okay. So
Yes, sir.
okay. So you were aware about the class. So maybe okay. So the next session will be on Friday onwards, okay? Because the last week I was having some conference, that's why I was not able to attend the session. But now we are in this week, we are having two classes. So one is already over today, and the upcoming class will be on, as usual, on Friday. So it will be on 25th. Okay. So on 25th from 7 to 9 again, we will be discussing the week 5 course. Okay. So I hope you will join. And today I think we have a little bit only discussion. So I hope next time you will join on time and we will have a great discussion. Okay. Okay. Thank you, everyone. Thank you for joining. And the recording and the PPT will be provided to you by the NPTEL team. Thank you.
Thank you, sir.